Okay, good morning. So let us continue our discussion about the inverse of matrices. So we learned about the inverse of a matrix, so I think this example we didn't do that. This might be a little bit hard example, but let us try to do it. Let A and B be column matrices of the same order such that A transpose B is not equal to -1. Show that I plus AB transpose is invertible and the inverse is obtained from this relation. First of all, tell me, do you think it's a typo here that I have written A transpose B is not equal to -1 or not? Because A and B are matrices, then I have emphasized that shouldn't be equal to -1. I just want to see, is that understandable? Yes?
Isn't it by default assumed that they're not invertible, or?
No, my question is different. So, no, by default is invertible. What did you say?
No, isn't by default, is it assumed that it is not invertible unless you can prove it?
Okay, but that's a different question, yes? I'm asking, why do you think, is it natural for you, for your eyes, or even you don't think about it? A transpose B is equal to if I give you a matrix A is equal to 5, is it strange or not after studying all these matrix theory? If I say that let matrix A be equal to 7, is it a little bit strange or not? No? Okay, why not?
I think we've said that we can have a matrix that's 1 by 1.
Yes, so that means that? Yes, so it is not strange, it means?
There's only one entry.
Yeah, so something like that. So when I say this, I mean this one, okay? So here when I say A transpose B is not equal to -1, so this should be strange a little bit to our eyes, unless we know that this matrix is 1 by 1. Yes?
Okay.
So usually matrices are block of numbers, not just one single number, yes? Okay, so when I say A transpose B is not equal to -1, do I really need to emphasize on that or not? Is it possible for A transpose B to be -1 or not?
I was wondering why does it have to be 1 by 1? Can't you have two separate matrices when multiplied become one term?
Okay, that's exactly, so I want you to talk about this. Yeah, it is possible. And that is happening. This might happen for this case. And that is why it is important to see that. Okay, A and B are column matrices, so it can happen, this combination. This combination is always a number.
Yeah.
And this might happen, this number becomes -1. I am excluding that scenario. I am saying that let us A and B be column matrices so that if you calculate this combination, which as Gustav mentioned is a number, that number shouldn't be equal to -1. So why is that possible? Because A is a column matrix, for example, say n by 1, B is also a column matrix, the same order, n by 1. If I calculate A transpose B, what do I get at the end?
1 by 1.
I get 1 by 1. Because A transpose becomes 1 by n, yes, A transpose, I interchange the row and column, so it becomes a 1 by n matrix, and B is n by 1 matrix. So when I multiply them, it becomes a 1 by 1 matrix. So it might happen, and I'm so unlucky that 1 by 1 number becomes -1. So I am saying that if that is happening, I do not have any claims. But if this is not happening, Yes, if A transpose B is not equal to -1, only under this condition, I plus AB transpose is invertible. And this inverse is proposed here. Okay, by the way, so assume that A and B are matrices of order n by 1. These are column matrices. What is the order of this combination? So for these matrices that you see on the board, A and B. So what is the what is this one now? What is the order of this matrix?
N by N.
N by N. Yes, because A is this one, and then you multiply it by B transpose, but A is sitting on the left this time, B is sitting on the right, yes? So if I want to multiply N by 1 matrix by 1 by N matrix, the answer becomes N by N matrix. So this is why I am asking you to show that this matrix is invertible, and I have proposed the inverse. So the problem could be hard if I ask you to find the inverse. But here the inverse is being proposed here to be I minus 1 over 1. This number is 1. This is identity matrix plus B transpose A.
It's
A transpose B times what?
AB.
Times AB transpose. By the way, this is a quite advanced problem. Might be you can consider it simply as a university problem, but I think you should be able to solve it. It is not hard. It's harder than the previous problems, but it is not that hard because the inverse is being proposed. So when inverse is proposed, your duty to show this is just to multiply them and convince yourself that the answer becomes I. And I hope that you understand that this is really number 1, yes? Because A transpose B is what? Is a number. According to the problem, A transpose B is not -1, so 1 over this makes sense, yes? And then we want to show that the inverse of this matrix becomes that. Okay, so let me start and then probably ask your opinion about it. So first, for proving this, I start with my matrix and I multiply it by the proposed inverse. Yes, A, B transpose. And I try to do this multiplication according to the rules of matrix algebra and convince myself that at the end it becomes the identity matrix. Of course, at this level, you have to redo it once more from the other side, but later, if we can cover it in this course, you will see that this is not needed. If one of them is satisfied, definitely the other way around is automatically satisfied, but it is not clear yet, because we don't know that this is always the case. Okay, so what should I do? You know that we haven't lost distributivity, so I can use distributivity. So what happens? I take I, multiplied by I, becomes I. Okay, I multiply I by this one. Don't let this distract you. If I ask you what is this in mathematics at the end, it is just a number. Yes? It's just a number. So when I want to multiply I by this combination, you can assume in your head that this is 5 or 7 or whatever. And then when I want to multiply I here, so this constant can be moved out and I will go and be multiplied here. But when I multiply I there, nothing happens, so I just have to rewrite it again. Yes? Okay, this is finished. Now I come here. I take this one multiplied here. This is a matrix multiplied by the identity matrix is the matrix itself. Okay, but then what happens here? I multiply this by that combination. First of all, I made a mistake. This is minus because one of them is positive, the other negative. And then when I multiply that, again for the same reason that this combination, whatever it is a number, So you know that if I want to multiply a matrix A by a constant times another matrix, this constant can float around. So I can pull it out and write AB. Yes? We had this before. So now this is playing the role of your constant C, this is playing the role of this A, and this is playing the role of that B. So this means that I can pull this out, yes, and then multiply this there. And you know that because matrix multiplication is associative, I'm not sensitive to put pairs of brackets around them unless it is necessary, but I'm sensitive not to rearrange the order, not to change the order. Okay, so then what? It is not that trivial as the previous example. I don't know how many of you remember. We had something similar I can show you. Last time, do you remember we had something like this? So, and then we started multiplication, the algebra was trivial, and I got identity matrix at the end. Okay, but this is a little bit non-trivial. So this is why I want you to now tell me what to do. Because my goal is to convince myself that everything will go away except I. Because my goal is to reach to I. And if the problem is properly designed and is correct, it means that the product should be I is already here, so this means that everything should cancel out. Okay, but why? Okay, so to guide you a little bit, at least you can do something with this part. Because that's a number, say for example -5, in your head assume that this is -5. So you have -5AB transpose, and then you have plus another AB transpose. What will be the answer? It will be -4AB transpose, yes? So the algebra here is simple. This is why I want you to learn in mathematics. If I ask you this, you immediately answer this. But for some reason, you don't do the same thing, and it becomes complicated. So this is something that I just draw your attention to it, but that is your own responsibility to teach it to your brain to think in that way, okay? So everyone hopefully could solve that problem, I'm 100% sure, but I want you to feel that's the same problem, yes? Because, for example, if I give you -1/5 AB transpose, let us see how many of you answered this one now. So what's the answer? Yes, because what you are doing, you say that in the previous scenario, I had -5 and I had 1, I added in my head, it becomes -4. You will do the same thing here. You have -1/5 of a quantity, you add one more of that quantity to it. So what is left for you? What is the answer? The answer becomes, in principle, you calculate this in your head and the answer is 4/5, yes? And then you say that, okay, this is 4/5 AB transpose, yes? Is that clear? So this is what I want you to learn in mathematics, because really, if you learn this step, to understand that these more complicated expressions are the same patterns that you have in your mind, it will solve a lot of problems for you. Okay, so now can you finally tell me what to do with this guy? Because now you understand everything, okay? So I have minus, let me just do it here, -1/1 plus A transpose B. I have A B transpose, and then I have another AB transpose. Yes?
You can write it as AB transpose, and then in brackets -1/1 plus A transpose B
Yeah, so it means that you have this number exactly as I had for -1/5. But this is important. This is written in a little bit fancy way, but this is at the end a number, so you can treat it like a 5. Okay, so this is exactly the same problem, but written a little bit more complex. Okay, so what did I do here? If I could do it in my head, I would do it. Otherwise, I go to scratch paper, calculate this number, and put it there. Yes, I have to do the same thing here. So what I am doing, actually, I am taking this number and this number 1 and add them together. Yes. And then I put this. Yes? Is that understandable? Okay, and then I have to simplify this. This is no longer a matrix or something. You know that this is a number and that's a number. I want to add them. In the case of 1 and -1/5, I was able to take the common denominator and simplify it. Here, I should also take the common denominator. Yeah, so what's the common denominator here?
1 plus A transpose B.
Exactly. This number is the common denominator. Okay, so this one will not change anything here, so it's -1. But this one will be multiplied here. And then I also have this matrix in front. This is just a number, but then -1, whatever, it is cancelled. And I get this expression, that A transpose B over 1 plus A transpose B times AB transpose. Yes, but again, what is this one you see here? Don't, because you know that in matrices we are not allowed to divide, but this is not division between matrices because essentially these are numbers, even though they are expressed in matrix form. Okay, so let us go one step forward, yes? So we combine these two. And the answer was plus A transpose B over 1 plus A transpose B, and then AB transpose. So I combine these two, but still this is left for me. So what can I do with that one? Always you need to think about what you're supposed to reach at, yes? You haven't lost the goal, yes? The goal is to get rid of everything except I. Because if this problem is going to be correct, what I am going to get at the end is I. So it means that I should be able to get rid of all these combinations. Okay, so in principle, you need to ask yourself, is it really equal to that? Because if this is going to work, there is no way this and that should cancel out. If they are supposed to cancel out, it means that this is the natural question to ask. Is there any way for me to guarantee that this and that are the same? Because if I can show that, then they are equal and they cancel out and I reach the goal. Yes, that's the way that you need to think. You have to be ready to actively interact with the problem, not just blindly do the things. Okay, so now you need to train your brain again like this. So I will more or less throw everything away from my mind, and then I focus on proving myself that this one is equal to that one. And if I want to prove that this one is equal to that one, what is my problem? The denominators are already equal, so don't let these denominators distract you. So the only thing here you need to convince yourself is what? So you see, this is the active way of solving problem, yes? So you go to a scratch work again. Your goal is to show that this is equal to that one. You already see that, okay, this denominator is exactly that one. So there is only one thing to convince yourself, yes?
Is it that AB transpose is symmetric?
No, don't jump into conclusions. Okay, might be symmetry will help you. But now just tell me, what is the first thing you need to prove? So you realize you have to prove this. One way to prove your problem is to prove that these two are equal. You check them, you see the denominators are already equal. So if you prove what, then you are done. Yes?
ATB is ABT.
ATB, no.
No, okay.
ATB is what? ABT?
Because it's
No, because no, this I understand what you mean, might be, that's also true, but that's not the natural step. The natural step is to, anyone else? The natural step is to, it's very natural for me, and it should be natural for you. This one is equal to that one.
Yes.
You want to prove the whole thing is equal to this one, so this means that this combination, yes? No, why 0? 0 is one possibility. But this combination, so might be this is something I have to fix in your brain, yes? For me it is quite natural, yes? I want to show this expression is equal to that one. I already know that the denominators are the same, so there is one way to prove that if I show that this is equal to that. Isn't it natural, or I don't know, might be this is natural for me, not natural for you, yes?
that's what I kind of meant, but I think that's because it's
No, don't, that's what I'm saying. Because this is a very important thing, because if you design the goal, even slightly different, might be you are not able to achieve that in one, because you are jumping ahead. So the first thing you need to think naturally, okay, I want to see this one is equal to that one. I already know that the denominators are the same, so I ask myself, is there any way for me to convince that this product is equal to that product or not? Yes? This is the natural thing for me. I mean, isn't it natural for you? Now you have to make it natural. If you cannot do that, then you don't learn mathematics. You cannot solve problems that easily. Because the problems usually are hard, and you're making it harder for yourself. Okay. So this is why I go to a scratch paper. So by the way, I really do these things. Okay, so I ask myself, is there any way for me to convince myself in a legal mathematical way that this is equal to that? So you see, now that question, the question actually is boiled down to answering that question mark. So this is a skill you will learn, okay? But still, mathematics is extremely hard, okay? But if you don't think in that way, there is no way, because you get lost in the calculations. And then you start, this is usually very common, people start randomly doing some calculations. Yeah. Okay, so that's the question. Is that understandable for everyone or not? If I can convince that this combination is equal to that one, then it means the denominators are the same, the numerators are the same, so these two damn things are the same, so they are cancelled. Okay, so now you need to focus your energy to only answer that question mark. Is it true or not? Okay, when you get stuck, it is important. This is something you need to learn. Go back and read the problem once more. Might be there are some assumptions you haven't used so far. So if everything goes naturally, you don't need to go back and forth and read the problem over and over again, yes? So when I'm doing this calculation, why should I go back and forth between the problem? I'm just doing multiplication, yes? But then I get stuck at some point. I would recommend you to go back and read the problem carefully once more. Might be there are some assumptions that you are overlooking, yes? So now I want to tell me, what is your opinion? By the way, the problem is not that simple because I do not have commutativity, okay? Because that's the only non-trivial thing in linear algebra, in matrix theory. Okay, now I want to hear from you. What is your opinion? Do you think that these two combinations are equal? By the way, is it a good way to say that, okay, Babak, you just taught us that, okay, I want to say that this is equal to this one. Because these are the same, if I succeed to prove these two are equal, then I am done. This is correct in general, yes, but you know that in matrix theory this might not happen. Yes, it might happen that the products are the same without the individual matrices to be the same. And this is why you need to appreciate, for example, I had examples that A is not equal to B, But when I multiply this A, which is not equal to B by C, and multiply B by C, suddenly they become equal. Okay? So might be, yes, you are right. If you succeed to prove this one is equal to that one, definitely it will work. But I would recommend you don't focus your energy on that, because it might be still possible that these two combinations are not equal, but after being multiplied by B transpose, they become equal. So if you just focus your energy to prove that this is equal to that, might be it is not the case. Yes, of course, if you can prove it, you are done. Because if you can prove this is equal to that one, this is also equal to that one, so this combination is equal to that. But if the question is hard, might be they have designed it in a clever way that this is not the case, but still the equality holds, because we have, if you know the properties, this is possible in matrix, among matrices. Okay. Okay, so let us use this experience, yes? So how do you answer the question? Yes, Hadi.
This is just like this, but if you check it, for example, A transpose is equal to A and B transpose is equal to B.
I mean, yes, if you can succeed to prove that, you are done. But the chances that you can prove it, I don't think it is high, because you don't know anything. First of all, A transpose cannot be equal to A in this particular problem. Why not? Yes?
They're column.
They are column matrices. So when you transpose them, a transpose of a column matrix becomes a row matrix, and there's no way for them to be equal. Yes? So you have to rule it out immediately. Yes, Alexander, did you want to say something?
One way might be to simplify by using that, for instance, A transpose times B is equal to B transpose A. You can use that.
No. Is A transpose B equal to
No,
B?
I mean like transpose of A times B is equal to transpose of B times A.
Yes, but why?
You can use that because you can simplify the left-hand side expression and the right-hand side expression.
No, I mean, which assumption helps you to conclude this? There is an assumption in the problem. So what you're saying, can you repeat it again? So what you said? To prove that?
A transpose B is equal to B transpose A.
Okay. So by the way, there is no rule in matrix theory guaranteeing this. Yes? This is a very odd operation. But Alexander is claiming this is true. And I agree with him. Okay? But you need to tell me why. And he also actually, yes?
You multiply by the inverse of ABT.
Still, we don't know. The matrix ABT is inversible.
Oh, of course.
Yes? But no, the problem is more than that. We had this before, but as a remark. But you didn't probably remember. But anyway, you did rediscover it yourself. But can you just tell me why this is true? First of all, is this a real matrix or is it just a number?
That's a number.
What about this one?
That's a number.
That's a number. So what you are claiming is these two numbers are always equal, even if you don't know A and B, yes?
I remember the rule. It was if you have two column matrices and you have.
Yeah, this rule works.
Yeah.
But why? It is, even if you have forgotten, it is not hard. So here, this is why I go back and read the problem again. Might be I have missed. Then I realize, okay, A and B are column matrices. I haven't utilized this assumption effectively yet. So there should be a reason they have put it in the problem. And if you understand that, then you come back and try to convince you about this. And this is clear because, for example, let me just make A to be a column matrix, say A1 up to AN, and let me have B another column matrix. So that is a behavior which is particular to column matrices. You cannot generalize it to all matrix theory. It's only working for column matrices. So I have B1 up to Bn. Okay, so if I ask you to calculate the left-hand side, you calculate the left-hand side by transposing A and then multiplying by B. You know what the answer is. What is that? You take the first one, multiply it by the first one, you continue doing this, and then you reach to the last ones, and then of course you know that you have to add them up. So this is the number you get by multiplying A transpose to B from the left. And what you get for the right hand side, this time you have to be transpose B first and then multiply it by A itself. But then what happens? B1 A1, and then you continue until Bn An. Do you agree?
Yes.
And then everyone knows that because these are just numbers, this combination and that combination are equal. So this is something we have extra when it comes to column matrices. So we cannot write a theorem for all matrices. No, this is not correct. Yes? But if they are column matrices, these combinations are the same. But do you think this will help for the problem here? Yes or no?
But there is a B transpose A in the right hand side.
There is an A transpose B. Okay, so what should I do? If I want to change it to B transpose A, does it work or not? Still, it's not that trivial, okay, but that's a good progress. Yeah, so we realized this is a number, by the way. Yes? Do you see any other number here?
B transpose A.
Yes, which is sitting in the middle. Yes? So this B transpose A, can I pull it out? Not always in all matrices, but here, yes, because B transpose A is just a number sitting in the middle in a disguised form. You cannot recognize that's a number there. Yes? So that's a number. Okay? So in principle, the left-hand side is this number multiplied by AP, B transpose. This is just a number. And because that is also a number sitting in the middle, the right-hand side becomes what? I can pull that number out, yes? And then I have this matrix left. But aren't they the same now? They are the same because this is the same matrix that appears. This number and this number are differently written, but according to this argument, they are the same. So the numbers are the same, the matrices are the same. So that is the product of the same number by the same matrix on both sides. Is that understandable? Yeah, I mean, so these kinds of, by the way, discussions are problem-solving workshops. So we set up a problem and start asking about the opinion about the problem, because I think these skills can be learned, okay? But creativity and IQ, unfortunately, probably you cannot increase it that much if that is true by research. But anyway, these skills you can learn and you can be a better problem solver if you pay attention. And by the way, memory really plays a vital role there. Okay, so I don't want to write it formally, but are you convinced now? Yes? So what I did, I multiplied them, I came up to here by those ideas, and then I asked myself, is there any way to convince myself about the question mark? And then we realized that, okay, we could, because this combination is just a number. This combination in the middle is also a number. By the way, this is not a number. This is not a number. But when I put them together, the combination in the middle became a number. And that is, by the way, relying on the associativity, yes? Because you have the product of four matrices, grouping them without changing the order is always allowed. So I decided to group these two together. Why is that? Because I realized that if I do that, it becomes a number. When it is a number, I can pull it out. Yes? Okay, so this way of thinking is actively engaging with the problem. Yes, is that clear? Okay, so now this theorem, again, do you remember we had this, the deviation from number algebra? I have already told you that if AB is equal to AC, there is no guarantee that B is equal to C in general. We had some examples in the very beginning of this lesson that we actually realized that AB equals to AC in general does not guarantee B and C be equal. But if A is an invertible matrix, then of course this is guaranteed. And the proof is so simple, but I want you to do the proof for me. So why is that correct? You see? So the question is this. We had seen this before. So in numbers, if A, B is equal to AC, even in numbers, this is not always guaranteed. Yes? Is it always guaranteed, even if I have numbers? No, under one condition.
A equals 0.
A shouldn't be 0. In that case, this is guaranteed. But in matrices, that's also more or less the same, because when you say A is not 0 in numbers, it means A is invertible. Yes, 1 over A exists. And that's the same thing here. If I give you matrix A multiplied by B is equal to matrix A multiplied by C, I cannot in general eliminate, cancel A from both sides and conclude this one, unless A is invertible. Yes? Okay. This is an extremely important condition. You have to check before jumping and canceling this out, you know? Okay, but the proof is extremely simple. How should I prove it? I give you this assumption that AB is equal to AC. I also give you the assumption that A is invertible, and then I ask you, why do you think B has to be equal to C? Yes?
If you multiply A inverse from the left.
Yes, am I allowed to use the notation A inverse here? Yes, because the existence of A inverse is guaranteed. Yes. So you told me that AB is equal to C. You yourself told me A minus 1 exists. A is invertible. So if this matrix exists, it's a matrix. The left side is a matrix, the right side is a matrix. Because you are telling me these two are equal, then we have to accept that this combination is also equal to that combination. Yes? Because A inverse is the same matrix, AB, you are telling me, is equal to AC. But we have associativity, yes? So instead of grouping them like this, I can put the pair of brackets around the first pair, and then I would say, I have this. And then you know that by the definition of A inverse, this combination is nothing except the identity matrix. And this is just identity matrix again. But you also know that identity matrix multiplied by any matrix is the matrix itself. So in that case, that's correct. But still, the content of that remark is this. If I have this, and I tell you that A is invertible, I guarantee you that A is invertible. Can you conclude that B is equal to C from this combination? So AB is equal to CA. It is guaranteed that A is invertible. Can I jump and conclude that, okay, so B is equal to C?
No.
It seems no, yes? And the answer is really no. I don't have the examples, you can cook up the examples, but I hope that you understand this method will not work here, because you need to decide. You are supposed to multiply everything by A minus 1, but then you have two options. Either you multiply from the left or you multiply from the right. If you multiply from the left, what happens? A minus 1 that you are multiplying will cancel this one, but A minus 1 is here. But then you are not in general allowed to interchange them. Yes? So you get stuck here. So if I give you this, definitely this is true, but I cannot go further. Because if I want to go further, I have to commute these two matrices, which is not allowed, yes? Unless commutativity of those matrices is also given in the problem, yes? From here to here, that's correct. Another way is to multiply A inverse from the right. Okay, in that case, what will happen? This becomes AB A inverse. In that case, A inverse will cancel that one. So this is true. Okay, this is also true. But in general, B is equal to C is not true. Okay, but what about this combination? If I have BA equals to CA and A is invertible, do you think I can conclude that B is equal to C?
Yes.
Yes, but this time I multiply A inverse from the right, and then I will have that one. So again, this I can conclude B is equal to C. Yes? Yeah, these are the things that you need to know very well. Okay, so let me also talk a little bit about the properties of the inverse. Usually I want you to have these rules in your memory. These are the rules of things, and then we will try to discuss a little bit about the proof, and then I think that is enough for today. So this theorem is actually contains a lot of items, so there are important things I want you to know. Okay, so the first thing is that the inverse, so assume that A is invertible, yes? Its inverse is also invertible. By the way, it's not trivial, you have to guarantee that, because the inverse of a matrix, if you have an invertible matrix, you know A inverse exists, but that becomes a matrix. And the question is that, is this new matrix is also invertible? This theorem guarantees the answer is yes, and it also gives you the inverse of the inverse is equal to A itself, is equal to the matrix itself. Don't take this for granted, yes? You say that, okay, the inverse of 2 is 1 over 2, the inverse of 1 over 2 goes back to 2. Okay, so the relation between the entries of a matrix and the entries of the inverse of the matrix is not that trivial. Okay, so even if I give you two matrices in front of your eyes, one of them is the inverse of the other one, and I do not reveal this to you, it is not that easy to detect, oh, this matrix is the inverse of that matrix. Okay, so if I give you 2 and if I give you 1 over 2, you immediately realize this number is the inverse of that. But I can give you two matrices, okay, that I have already known. I already know that they are inverse of each other, but I put them in front of your eyes, okay? By looking at them, it's not that easy at all to realize this matrix is the inverse of the other matrix. So you treat them as two independent matrices. So this is why this is not just talking a lot. So if you want to be expressing it precisely, you would say that if A is invertible, the inverse becomes a matrix. This new matrix is also invertible, and the inverse of this new matrix is the original matrix. So the inverse of the inverse is equal to the matrix itself. By the way, why? So you want to prove this? Yes?
For the inverse of A, the inverse of it is the inverse of A times its own inverse is supposed to be equals to the identity matrix, meaning that and there is only one matrix that can do that, which is A.
Why? Because we proved that.
Yeah.
If the inverse exists, that is only one matrix. Yes, it is unique. So that is crucial. So if we didn't have that one, we couldn't say this one. Yes, you are right. So another way to look at the problem is this. Where is this? I think up here. So in other words, what you are saying is that I want to show that if A is invertible, of course, I want to show that this matrix is invertible, and its inverse, by the way, is being proposed. Yes? So I told you that when the inverse of a matrix is proposed and you want to prove this is true, it is extremely simple. What should I do? I need to multiply my matrix by the proposed matrix and show that this is the identity matrix. Is that clear? So here, I am proposing the inverse of this matrix to you. And you are supposed to confirm that. So remember this, don't forget about this. So if I want to confirm that, it is necessary and sufficient to prove that this can play the role of the inverse. This is the proposed inverse of this matrix. So what I need to show, I need to guarantee that if I take the proposed matrix and multiply it by my matrix, it becomes I. But is it true? Yes or no? Yes, because of A inverse, yes. So I mean that is exactly the definition of the inverse. I don't want to confuse you, but this is the real way to understand that. If you think it is trivial, it's not trivial. Okay? So if you can discuss about that. So I am proposing the inverse of a matrix to you. For example, if I ask you to show B inverse is equal to A, I told you what to do. You take the proposed matrix for the inverse and multiply it by your matrix to see if it is I or not. I did the same thing, but the only problem is that this is playing the role of B. I want to show that the inverse of this matrix is A. This is the proposed inverse. This is my matrix. To guarantee that, I have to take the proposed inverse, multiply it by my matrix, and see if this is true, it becomes I. But is this equality true or false? True, yes, because of A inverse. That's it. That's the proof. Okay? Go back to the next one. If A and B are invertible matrices, this tells you that A inverse is equal to B inverse if and only if A is equal to B. So if A is equal to B, their inverses are equal, and if the inverses are equal, they are also equal. You can think about this yourself, okay? It's very simple. Okay, the next one is also very important. I have a real number which is not zero, it's a non-zero real number. I multiply it by an invertible matrix. This is claiming that the new matrix is definitely invertible. And it is also proposing the inverse. It's a very nice relation. So if you have a number multiplied by a matrix, you want to take the inverse, you inverse the number in the realm of real numbers, means 1 over r, and then you inverse your matrix and then multiply it. Yes? Why is that? So my question is this. R is not zero. A is invertible. I want to guarantee that R times A is invertible, but more than that, I want to show that its inverse is equal to that one. So how should I prove this?
If you multiply the...
Exactly, that's the same rule. You have to be quick in this, because I'm proposing inverse to you, and you want to confirm this is true. There's only one way. Not one way, this is the best way, yes? To take your proposed matrix, to propose inverse, and multiply it by your matrix to see if it is I or not. Yes? Oh, sorry, I wrote it wrong. Yes. So, what I do, I will take the proposed matrix and multiply it by my matrix, which is RA, and see if this is equal to I. Okay, but I am allowed to use the matrix algebra. 1 over R is a number, we know that numbers can float around. So what I do, I will take them together, it's 1 over R times R, and then I put the matrices together. But I know that R is a non-zero real number, so I know this combination is number 1, and A minus 1A by definition of A inverse is I, and then 1 times I is just simply I. That's the proof, yes? By the way, with this way, I also prove invertibility and this one, that this formula is correct. Okay. Okay, let me repeat this again. But this is these two items are extremely important in matrix algebra. So what does this tell you? It tells you that if you have an invertible matrix A to start with, you transpose that matrix. The transpose is also invertible. And the inverse of transpose is the transpose of inverse. Yes? So that is important. So this formula tells you it doesn't matter if you transpose first and then find the inverse, or if you find the inverse first and then transpose. It is not trivial, by the way, at all, because the matrix algebra is not that trivial, especially if you know how complicated it is to determine the inverse. We haven't talked about that yet. Okay, so why this is true? Why A transpose? Let me write it here. You can think a little bit. So you shouldn't take these things for granted unless you have a proof. So this tells me that if A is invertible, then it doesn't matter if I transpose first and then take the inverse of the new matrix. Or if in the beginning I find the inverse of my invertible matrix, it becomes a matrix, then I transpose them. These two are equal always. Why is that? You don't listen to me, yes? You should be a good listener if you want to be a good learner. Yes?
You multiply.
Exactly. So I'm proposing the inverse of a matrix to you, yes? I am telling you that, guys, the inverse of this matrix is this one. You want to confirm that. So this is why you need to teach yourself. I'm just drawing your attention to it because these will play a vital role in your brain, you know? You make new circuits in your brain to appreciate these, yes? Isn't it the case? Don't let the complication distract you, yes? This is at the end a matrix. I am claiming the inverse of this matrix is this. So I am proposing the inverse of this matrix. Your duty is to confirm that. It might be hard. I'm not saying it's always right, but the starting point should be a matter of seconds. Yes? Just multiply. Multiply what? The proposed inverse. Yes? By your matrix. What is your matrix?
A transpose.
A transpose. And ask yourself, is there any way that I can confirm this? Do you understand that? So that's the same thing. But is it possible to confirm that? Now, memory plays a vital role, yes?
You can transpose both sides.
No, because we don't know it yet. If you transpose both sides, it means that you already take this for granted. And of course this will work. You can transpose both, you get to an equality, which is true, but then you have to be careful. Is it possible to go back? Yes, whenever you start with tampering with your the one that you want to prove and reach to a statement which is true, you have to be sure that you can come back. If that's true, then the proof is complete. Okay? But better than that, this combination TT, this you should have it in your memory because I emphasized that this is also important when I was teaching you the transpose, yes?
Yeah, can't you pull out the T? Like as and A to
Could we? Yes or no?
It is.
So, for example, A transpose, B transpose. Can I write AB transpose? Pull it out.
Well, no, you have to flip it.
Okay, that's it. You have to flip. So you can do that. So this is not correct. A transpose, B transpose. If I want to pull this T, the price that I have to pay is to interchange, and that is extremely important. Okay, so here I can do that. So I start from the left-hand side. My goal is to pull T out. Yes? And then what happens? The price that I pay, I have to rearrange them, yes? So A goes here, A inverse goes there, but it doesn't matter actually, yes? This change of order doesn't matter because A times A inverse is also I, and then I have I transpose. But what is the transpose of I? I itself. And this is the right hand side. So I was able to confirm that. So the proof is extremely simple, but this is a very extremely useful result. Okay, so one more and then we'll stop. Again, another extremely important formula, yes? And this is A, B are invertible matrices. We are claiming that, okay, in that case, the product is also invertible, but the inverse of the product is similar to the transpose. You have to flip the order. So it becomes B inverse first and then multiplied by A inverse. Okay? So why is that? So I want to show that if A and B are invertible matrices, A and B are invertible, and then I want to show that AB is also invertible. More than that, AB inverse is B inverse A inverse. So it is very similar to the transpose operation. So you can put this on top of them, okay, and then you need to do that. On the other hand, if I want to take this minus 1 out, I need to remember to reorder it, yes? Okay, why is this true? Yes?
You multiply.
Exactly, so now it is clear. So I have proposed the inverse of a matrix to you and you want to confirm that, yes, that's easy. So you take the proposed inverse and then multiply it by your matrix and ask yourself, is it true that this is I? If I can confirm that, then I am done, yes?
You group A minus 1.
Yeah, because we have associativity, yes? Instead of grouping them like that, so I will start from the left-hand side, I would write B inverse, and then I write A inverse A, and then B. But A inverse A is I, so this becomes B inverse IB, but this becomes just B inverse B, and this becomes finally I, and that is the right answer. Okay? Okay, good. So I will stop here because I gave you a lot of information today. What is this remark? Okay, this remark is also, okay, so let us stop at this remark. So that is a good idea that we start this later. Any questions? Okay, thank you.